Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, it's a pleasure for me to introduce Andrew Davison. He's a reader in robot vision at Oxford or at Imperial College in London. He is an old friend and colleague of mine, so it's really great to have him here. He studied physics at Oxford and graduated first class honors in '94. And then he started in the robotics research group in Oxford and did a PhD with David Murray. And he then created one of the very first vision-based SLAM systems. SLAM is Simultaneous Localisation and Mapping, solely based on a single camera moving. And that has been working and improving on that ever since. He graduated and went to Tsukuba University for 2 years in Japan, working more on visual robot navigation. And then came back to Oxford for a while, but then moved to Imperial College to be a lecturer and then now a reader. So please help me in welcoming him. Thank you.
Okay, thanks very much for the introduction and for inviting me here. So I'm going to talk to you about, well, really what I've been working on over the last 5 or more years. So this general problem of real-time visual localization and mapping with a single camera, and tell you a little bit about where this research has come from and then what we're doing at the moment and what we're trying to do in the near future. So the general goal of all of this, I mean, it's something that a lot of people are also thinking about, but can we turn a simple camera into a general real-time 3D position sensor, so just a webcam like this connected to a laptop or other kind of computer, and you'd ideally like to be able to just go anywhere with that camera, do real-time camera tracking and build a 3D map or model of everything that you've seen. So I mean, always kind of fundamental to everything that I've been trying to do is this real-time constraint. So I'm really talking about hard real-time, so 30 hertz or more. So the demos I'll show you all run at 30 hertz here. So there's a real difference to the way that you can think about tackling problems when you've got that as a constraint. So we all know, or I expect you all know, a lot about structure from motion and research in vision, taking multiple images and trying to reconstruct the positions of the cameras that took those images and something about the structure of the scene. But classically, those were batch methods. So you take a set of images, you know, you've loaded them in off your video camera, or they're a set of discrete images, you process them and you make a reconstruction where you've got the estimated position of the cameras that took the images and an estimated structure of the scene. So for real-time applications, we need to do that processing sequentially. So we really want to be updating step by step. As we get a new image in, we're updating our estimate of what's going on. So it's clear that there's a class of applications where you need to run in real time. So there are some very nicely well-established offline applications for camera tracking, particularly in like movie post-production, for instance. But if you want to do things like robotics, then you need to be able to do this in real time. So that's where my kind of interest in this started. I was working on robot navigation using vision. But you know, I'd like to come up with really quite general technology for robot localization and mapping, where you can really just have this camera type sensor that you can pretty much put onto any type of robot and off you go. It's got a localization and mapping sensor. So particularly for robots that move very dynamically, perhaps they fly, perhaps they're humanoid robots. Or there's this other very interesting area of low-cost type of robotics for consumer level applications, where you want something very cheap and kind of simple in hardware terms. You don't want to have to put a lot of extra sensors on there. So beyond robotics, there are other applications, so things like wearable cameras, or these types of cameras which so people have started to do computer vision things with these cameras, but so far they're relatively simple. I mean, if you can really start picking up these cameras and moving them around through spaces and doing real-time tracking and mapping, then I'm sure there's going to be a lot of interesting things you can do. So in all of these systems, often you've only got monocular video. I mean, in some advanced robotics, you can certainly have stereo or in other applications as well. But let's assume that we've only got monocular. We've got relatively unconstrained motion, high acceleration, large rotation, and generally we're not going to have any other sensors giving us priors on the motion like inertial sensors. We'd just like to try and do everything using vision. So I should definitely mention, my approach here is not the only way to tackle these problems. So there's a particularly successful alternative path, so I would say really pioneered by David, but there are also a lot of other people working now on similar ideas. So if you want to do real-time camera tracking, then you can't tackle the whole structure from motion problem. So basically, it's quite well known now that to get the optimum solution to a structure from motion problem, you take all of the images you've ever taken, you match as many features as you can over that sequence, and then you do an offline, well I say offline, but you do a global optimization. You can try and find the optimum set of estimated positions of the cameras and estimated positions of all the features you've ever seen to try and get to bring those into the best alignment with what you've actually measured. So that's what's called bundle adjustment normally in structure from motion or photogrammetry. But you can't just tackle that in real time and just keep extending it, i.e. you can't do a global optimization based on your first 100 images and then get one more image and then go back and globally optimize everything again. Because as you get more and more images, the amount of processing time per image you're going to have to spend on that will grow. So you've got to approximate or sparsify in some way to make something run in real time. So one approach which has been very, very successful is to think of, let's keep a kind of optimization approach. We'll keep matching lots and lots of features, but we'll restrict any optimization we do to a kind of window starting between now and some fixed kind of time in the past. So you might call this sliding window bundle adjustment, for instance. So you take your last 100 frames or whatever window you can process in real time, and then you can from that get very, very nice local motion estimation. So very accurate local motion estimation, very good local estimation of the positions of all of the features relative to that trajectory. So David's work in this was very, very nice. So these are some trajectories of a robot driving through a forest. I believe this was with stereo, wasn't it? Yeah. But this is a comparison of the visual track against GPS, and a very low level of drift here. But you will get some drift unless you do something to correct that. So i.e., if you want to make this globally optimal, when you come back to old places, you've got to recognize them as places you've seen before and correct any drift that's built up. So actually there have been some really nice papers in the last couple of years showing how you can do that. So particularly Kurt Connellige has done very nice stuff, and then there's been very good work by Klein and Murray in Oxford showing how you combine a kind of visual odometry approach with keyframes. So you select some of the frames from your sequence and then do a kind of global optimization on the basis of those. So you link your kind of local visual odometry tracks to those keyframes and globally optimize the keyframes, and you can do a very nice job. So as you'll see, the approach that I've taken here is a bit different. Yeah, sorry.
How much is known about the trade-off between the amount of work you do and the quality of the result?
I would say so far maybe not very much. So, I mean, as I'm going to say later on, that's probably the main thing that I'm really interested in investigating now. So I'm not saying that what I'm doing is better than this. In fact, I've come to think more and more that I'm really understanding the advantages of this method. But I'd like to explain you my kind of approach to this and how I think it relates to that. So I've really tackled this problem of camera tracking as an example of simultaneous localization and mapping. So in the robotics community, this SLAM problem is understood as the general question, the general problem that a robot faces when you put it down into an environment that it doesn't know in advance, and it's got to basically navigate autonomously around that environment. So it's got to build a map and localize at the same time. So it doesn't know what the environment is in advance. It doesn't know its motion in advance. It has to estimate both simultaneously. So there's been a lot of really nice work in this SLAM area in the last few years as well. So here's just one of many videos. So this one is by Paul Newman's group in Oxford. So maybe the key point is that a lot of work in SLAM until the last few years has not used vision as a primary sensor. So this was done with a scanning 3D laser rangefinder. So generating very accurate 3D point clouds, registering them, and then trying to estimate the global map and motion of the robot relative to that. So I've basically tried to adapt some of the methods used in SLAM to this camera tracking problem. So people in SLAM now have come to this same kind of general and probabilistic understanding of what the scope of the SLAM problem is, and you can pose it as a Bayesian network like this, where the things that you want to estimate are all the places that your robot has been, so the poses of your robot that we'll call X, the positions of all of the features that you're trying to measure. So feature here as a general term, it could be a point, it could be a plane or a line or anything that you can repeatedly measure. But these things aren't directly observable. The things you observe are these measurements. So every measurement is like the image position of a feature in a camera, or the 3D scan of the position of some line. These are the things you can observe. You have to eliminate these from the network and estimate these things that we're interested in. So also in a lot of robotic SLAM problems, you've got some other information coming in, which might be odometry information. The robot knows about the wheel turns, or it's got inertial sensors or something. So you can integrate all of that as well. So this is very similar to bundle adjustment, basically, where you haven't got these, but you've got the measurements, and you want to solve for these. So the way to get the global optimum here is it's clear. You just have to eliminate everything from the network except the things that you want. But the way to get real-time solutions are, to tackle that not in a global way, but in some sparse or approximated way. So people in SLAM have come to understand very clearly now that the different approaches, so Kalman filtering or a visual odometry approach or other types of things, are different examples of ways of eliminating variables from this network, if you like. So the approach that I've taken is really the classic approach to SLAM, which now is by no means the only approach, but the filtering approach. So that means let's just try to always estimate a PDF over the current position of the robot or the camera and the current positions of the features in our map. So at some snapshot point in time, we have a PDF over the things that we're interested in, and we'll try and sequentially update a PDF over those things over time. So it's like at every step you're eliminating everything from your network but the last pose of the camera and the poses of the features that you're observing. You'll marginalize everything else out. When the robot moves again, gets a new image, you add a new pose here, and you eliminate, marginalize out this one. and you'll be left with a PDF over this, and these things are joint PDF, and you continuously update that PDF. So in a kind of simple SLAM problem, this is what it looks like. At any snapshot in time, we've got an estimated position of our robot or camera, estimated positions of some features. All of those have some uncertainty. The uncertainty between the different things is correlated, and then you update that probability distribution in 2 looping steps. So whenever you have this kind of movement, so a blind movement in between measurements from the outward looking sensor, you update your estimated position of the camera or robot, and the uncertainty in that will increase, because even if you've got odometry or some other sensing, you'll be less certain about your position after that than you were before. Then when you turn your sensor and make some measurements, so in the vision case this is making image measurements of features, you get information, you reduce uncertainty. So these ellipses shrinking means that uncertainty is shrinking, is getting smaller. So over a long period of time, if this robot moves round and round, make lots of measurements, the uncertainty on all the feature locations will provably eventually shrink down to 0, and you'll converge to a perfect map. So this was my first experience of kind of implementing this. So this is my PhD thesis work with David Murray in Oxford, where we built what was probably just about the first real-time SLAM system that used vision as the primary sensor. So here it was fixating active stereo, measuring point landmarks like the corner of this box, and on every time step selecting which is the best feature in the map to measure. So you'll see it keeps coming back to look at the same things repeatedly. It's running a Kalman filter to estimate the correlated positions of the robot and all of the features that it's seen. And we build these kind of maps where we're estimating the position of the robot quite accurately, and then these are uncertain estimates of the features that we've seen. So some of those that we've seen many times we can get very accurate estimates for, and some that we haven't measured so often, or we've measured from a long way away, we've still got relatively large uncertainty. Okay, so from now on I'm going to talk,
So it looks like you kind of, at least in this work, zeroed in on the Kalman filter, extended Kalman filter. It kind of commits to the mode, right? As opposed to all these particle filtering things that are popular with, I don't know, Thrun and Fox and things like that, where they think, oh gosh, we have to have thousands of hypotheses because we could be way off. Do you have any comments about that?
Yeah, I mean, I think actually, so there was a period when particle filters were very popular in SLAM, but I actually think people have backed off from that now, and there are big limitations with what you can do with particle filters as well, because yes, they allow you to represent, multiple hypotheses explicitly, but again, if you want to run in real time, you've got a bounded number of particles, and in fact, so in something like fast SLAM, I don't know if you know about that, that's the classic way of applying particle filtering to SLAM. You have particles basically representing trajectories of the robot, and what you find is as you try and make long journeys, your uncertainty grows so much that your particle distribution kind of becomes a bit too sparse to really represent discrete multiple hypotheses. So I think now that the state-of-the-art methods, they're not EKF, but they're Gaussian based basically. So things like graph SLAM type of methods. Yeah, sure. So specifically talking about this single camera problem, so it's an example of SLAM. It's a moving sensor measuring uncertain things in the world, trying to build a map. But it's more difficult than most of the problems people have studied and called SLAM. So in particular, it's in full 3D, whereas a lot of SLAM researchers just had robots moving on planes. We've got this bearing-only measurement of features, so that means a camera obviously only measures angles, doesn't measure distance, unlike a laser rangefinder or a sonar. Usually we've got no odometry. We want to run at a high frame rate. So those are kind of the things that make it hard. But on the other hand, in a lot of the practical applications that I'm interested in, so if in the case where you've got a camera flying around in a room and you're trying to do augmented reality, for instance, or you've got a domestic robot moving around in a house, you've got this fairly limited environment with repeated motion. So that's more the case where my approach might give you a win over the visual odometry approach. So there's often an emphasis on real-time localization rather than really getting very dense information about the environment. So that may or may not be important. So therefore, fairly sparse mapping may be sufficient. So you'll see that in my approach, we're not reconstructing real detail about the scene. It's really just a map of landmarks that tell us where the camera is. So here's just a few details about how this basic system works, so which we call MonoSLAM. So we're going to build a map of point-like features. So these are fairly standard image features. So we actually use Shi-Tomasi detector, very similar to Harris type of features, but with kind of larger image patches than would normally be used to make those features a bit more distinctive. So we detect candidate features in images like this, and then we incrementally add them to our Kalman filter based map of what's going on. So this is, the image view. This is like the 3D current estimate of what's going on. The camera's here and it thinks these features are here. So one of the key novel things about this work is the way that we measure features. So in contrast to most structure from motion or other vision type systems, we're not doing feature detection on every frame. We're detecting new features once, and then after that we're matching them with what I call active search. So that means that when we get a new image frame, we, based on the estimated position of the camera at the last frame, we apply a motion model to that, which gives a kind of estimate of how much the camera might have moved in that period of time. So now we've got a fairly uncertain estimate of where the camera is now. Based on that, we predict which of the features in our map should be visible, and we predict where in the image we should be seeing them. So we can predict not just the mean positions, but also a distribution. So for every feature, we can define a search ellipse like this. So this is like a 99% confidence interval, 3 standard deviation. So we're pretty sure that unless something really weird is happening, unless the camera suddenly jumped to a different position which breaks our motion model, we should find this feature somewhere within this region. So therefore we search for it by applying an exhaustive correlation search for our template just within that region. So obviously, practically at fairly high frame rates, these regions are small. So we really win here by keeping the frame rate high, means these regions are small. And obviously we can then do all these searches very rapidly. This is one of the main things that makes it fast.
What about occlusion?
So, I mean, that will probably, you'll see that in the demo later on, I think, but features that get occluded, hopefully correlation doesn't match well enough above a threshold, and we just throw that measurement out. And eventually, if it's occluded enough times, we'll delete the feature from the map. So also, we actually, for a long time, we were running this without any kind of robust throwing out of feature matches that weren't right, because you don't get many mismatches when you do this, because every search, you've got the kind of global consistency already imposed. All these matches have to be fairly consistent. They have to be consistent with the search region. So, and the features are fairly unique anyway. So we don't get many mismatches when we're doing this, but we do get some mismatches. So we can apply a step afterwards, which then prunes out the few mismatches we get. Yeah.
One of your features is at the intersection of two objects at different distances.
Yeah.
So that produces sort of the synthetic feature that isn't anywhere in the actual world. Does that get destroyed the same way?
Usually you would hope that feature gets deleted because it's not geometrically consistent with the others, but I can't say that always happens, because we've got a relatively small number of features here, sometimes features like that will live on and introduce some error into the map. So another thing we can do that's part of this active approach is we can match features which are upside down, for instance, by pre-warping the image templates. So we don't need to use something like SIFT, which has this invariant property built in, because when we're continuously tracking, we can just predict that this feature should be upside down, and therefore we flip the template upside down before we try and match that feature. So again, that's super efficient. So here's our camera and map parameterization. This is very straightforward. So the features are 3D points. The camera, we estimate its 3D position, a quaternion for its orientation. We also estimate its velocity and angular velocity. So all those things go in the Kalman filter. So we need to estimate the velocity in particular because that forms part of our motion model. And our motion model says it's basically a constant velocity kind of motion model that says we assume bounded Gaussian distributed acceleration. So if the camera's here, where will it be on the next frame? Well, it definitely won't be there unless something very strange has happened, but it could be here or here or here. It might have speeded up a bit or slowed down a bit or accelerated a bit to the left. And the final kind of part of this, which was one of the trickiest things in initially getting it working, was how to initialize features into the map. Given that we've only got one camera, we can't initialize features after one frame properly, because after only one measurement of a feature we don't know anything about its depth. So initially, when I first got this working in 2003, I used like an auxiliary particle filter to initialize the depths of new landmarks. But something that we've done recently is to change to a parameterization of inverse depth for features. So this is kind of probably almost obvious to structure from motion people that you filter on disparity rather than depth, and you get high Gaussianity in inverse depth coordinates. So, well, this is a video, but I think I'll try and run this live now, just to give you a good idea of how it works. So this is the kind of the basic system from 2003, but with some kind of newer developments that make it a bit better. Okay, so here's our 30 hertz sequence. So I start tracking, and you'll see immediately that we're tracking quite a lot of features in the image here. And in the 3D view here, we're now estimating 3D camera motion relative to this map of features. So just to explain to you a bit more what's going on here. So some of the things you'll see, there's a green box flashing around, which is basically hunting for new features. And you'll see it's trying to hunt for features in places where there aren't existing features in the map. But it's only on every frame, it's only searching a fairly small part of the image. It's not doing feature detection on the whole image. So it's fairly kind of content at the moment. It's got a lot of good features. So just to show you some more things about the features. So here you can see the actual image patches that we're tracking. So they're relatively large patches of the image. So the colours mean red is a successfully matched feature on this frame. Blue is one that we've tried to match and failed. Yellow is one that we just haven't selected for measurement on this frame. So generally, because it's too close to the edge of the image, I think is the main thing that's going on here. So you can see that even if we're not measuring these features, we're predicting their appearance. So if I start turning the camera, you can see that for this feature down here, the thing in the patch is actually rotating because we're pre-warping to predict what that feature should look like. Okay, so here's the here's the camera pose. And then as we start kind of moving more and exploring new areas, you'll see it more aggressively kind of trying to initialize new features and expand this this map. So you can see the kind of inverse depth representation of features here. So we can have features at a wide range of depths in our map. So a feature here that's just been initialized, we have a very large uncertainty on its depth until we move the camera enough to actually measure parallax, and then we can estimate the depth of that feature properly. It's kind of working reasonably well in here, but not fantastic. Let me just see if this is going to work. No. So I can rectify the image. So that means taking radial distortion out of the image, and then we can use this to do augmented reality and put virtual objects into the view. But I think that's not going to work for me today. Okay. Anyway, so let me just stop there and continue with the talk, and maybe we can come back to that later. Okay, so we can look a little bit at the performance of that and try and think, why does it make sense to follow that approach? So some of the good things that are going on with that feature is we're mapping features sparsely, but we're able to treat each feature fairly carefully and try to make this sparse map of fairly high quality features. So they're high quality, first of all, in the sense that because there aren't that many of them, we can do a relatively large amount of image processing work for each one. I mean, I think that's something we haven't taken as far as we could yet, but we can do warping, we can have fairly large templates and so on. We have this active search guided by uncertainty that's really meaning we're able to measure these features very efficiently based on prediction. And when compared to something like visual odometry plus keyframes, where basically your estimate of a global map is relying on those keyframes, in this filtering approach we are able to integrate information from all of the images into a single consistent map. So these are some figures from a few years ago. So this was comfortably running in real time, on a laptop 5 years ago.
It seems like the obvious
Yeah.
device to run this is a mobile device or a phone.
Yeah.
How far away is that real time on a phone?
I haven't tried it. I mean, I think it's possible that you could get it working. Yeah. So I've been thinking more in the direction of let's try and make it run really, really, really fast. So something I'll show you in a second is so it's trying to run it on a 200 hertz camera. But yeah, I think the real advantage here is you can make this very, very cheap. Yeah. Yeah. So when you have multiple processors, what would you do? It's perhaps not as completely obvious how to parallelize this as it is something, some other vision algorithms, because it is quite kind of tightly looped the way it works, in that we predict where we're going to measure the features, and then
Feature search is obviously parallelized.
yeah, okay, but that's relatively cheap anyway, I think. I think the thing you'd really need to, yeah, I mean, I think these figures are somewhat out of date, that this could now be, clearly below a millisecond. The bit that really kills you in this is this the filtering part. So on every frame, you're updating relatively large matrices representing the uncertain correlated positions of all of your features. So certainly it is possible to think of breaking down those matrix calculations into blocks and parallelizing those. So I think that would be the thing to attack if you wanted to, if you did have multiple processes.
So the common filter update this is basically a dense block that corresponds to 3 times the number of features plus the camera parameters.
That's right, yeah. And in the filtering thing, there isn't explicitly much sparseness in there, but still you can break the multiplication and stuff that you're doing up into blocks that you do separately and then compose later on.
It seems like if you really want to put this into a toy or a cell phone or whatever, and it's wonderful, it would also be interesting to understand something about what the power consumption trade-offs are.
Absolutely, yeah, absolutely. Yeah, so I think all of these questions really, speak towards what I'm really been thinking about recently, which is how do we really move towards the ultimate performance in these kind of systems. So there's this approach which is fairly successful, there's other types of approach which have also been successful, but how do we really find out what's the best way to tackle these problems? So I think there's a number of trade-offs which we can consider here. So frame rate, the number of features that you measure per frame, the number of frames that you try to track the same features over. So do you just have lots and lots of features tracked for a few frames and compose all of that, or fewer features tracked from more frames? You're going to get a different result by doing those two things. I don't really know the answer yet of how much better one is than the other. Image resolution, for instance. So I could use a higher resolution camera. So if I've got double the processing power, I could double the resolution, or I could double the frame rate. I don't really know the answer to what's the best thing to do there. Field of view of the camera. So something we experimentally found was this worked 10 times better when we increased the field of view of the camera from 40 degrees to 90 degrees. It made a really big difference. So omnidirectional should be even better, but then as you increase resolution, if you've got the same number of pixels, you're losing angular accuracy. So I think that there's more trade-offs there, but I think I really want to investigate these things. So the currency of these trade-offs is processing time. So we want to look at the accuracy of the map, but we want to trade that off against how much extra processing time is involved. So if we increase the resolution, for instance, then the same size search region will cover more pixels, and we're going to have to do more image processing work. If we have more features in the map, our kind of back-end estimation work will be increased. But I'm really interested in trying to find some optimal kind of things about what's the best way to tackle these problems. So I've got a new project now which is really looking at these kind of things. So we want to make camera tracking more efficient. And I would say that more efficient, it certainly can mean you can run it faster. It would certainly mean you can run it cheaper on a cheaper processor, but it also means you can ultimately do it better, because if you can basically do all the same things in half the processing time, then you've got that other half of the processing time which you could use to make it better. So I think making something more efficient is a fundamentally important thing to try and do. Yeah.
Consider another concept might be interesting, which is special purpose hardware. Because sometimes there are things that you can do much more economically.
Yeah. So
and those vary a great deal depending on what the nature of the computation is. So.
Definitely, yeah. And I think in some ways that's why one of the weaknesses of this is that we've considered this tightly coupled approach which aims, for instance, to minimize the amount of image processing you do. But then, people come along with special hardware, or they're doing stuff on graphics cards, and actually you can match thousands of features in an image at frame rate anyway, just using that stuff. So
I actually wanted to suggest that you might want to look at more from first principles and not ask what can I do on a graphics card, but what can I do with gates? Because if you're really going to put this into toys, you could definitely afford to engineer that kind of thing. And asking what you can do with a graphics card might not be the right
question.
Understanding of what you can do with gates.
That's very interesting. Yeah, absolutely. I think if you think about the human visual system, so I would say most of the things in this system, they're top down. So It's thinking about what we want to get out of an image and then very specifically going in and trying to pick out those parts. But then human vision shows us that there's some things we do top down, but there's a lot of stuff we do bottom up. So where do those things really meet? Which things are worth doing top down? So by doing a lot of filtering, you can predict exactly where to look in an image to get what you want. But maybe in the processing time you've spent doing that filtering, you could have just detected all the features anyway. So yeah, I don't have a good answer to those kind of questions yet. Okay, so thinking about the directions that we're going in with ultimate performance. So this is a video that's kind of inspired me a lot over a long time now. So this was about 10 years ago at the University of Tokyo, where they actually then made a custom 1 millisecond vision chip. So it could only grab a very simple image of 16 by 16 resolution, 1 bit per pixel. So it could basically track white balls against black backgrounds, but very, very fast. So just to show you the kind of, the really nice things you can do with that high frame rate system. So one of the things that opens up is something that's been used relatively little now, actually using vision directly in robot servo loops. So if you've got, for instance, a balancing robot like a humanoid or something, those robots can balance because they have very high frequency servo loops measuring sensors like force sensors and torque sensors and inertial sensors. They're measuring those at a very high frame rate and then able to balance. But if they do have vision, that's coming in at this much lower corrective kind of, coming in at 30 hertz is not much good for balancing. But if you can do vision at multiple hundreds of hertz or 1,000 hertz, you could directly, servo in on things or have things thrown across the room and controlled and so on. So I had a bit of fun recently, kind of trying to come up with some target image sequences that maybe we'd like to track. So do real-time kind of camera tracking on a sequence like this. So if you slow this down at 25 hertz, this looks pretty hard to me. So you've got very big jumps from one image to the next. So I've even, I've tuned the camera to knock out most of the motion blur, but in other cases there would even be massive motion blur. But it's going to be hard to do any kind of frame-to-frame tracking on images like this. But here's the kind of obvious next step. So this was actually subsampled from 100 hertz video, and you get this much nicer kind of dreamlike smooth quality to the images. So I think there's a very nice opportunity for where this active kind of approach, this top-down approach, seems to fit in very nicely with trying to track high frame rate sequences, because you get a nice kind of scaling. So any bottom-up vision processing that you're doing, feature detection and so on, if you're doing that, the same thing on every frame, then clearly the amount of work you have to do scales proportional to frame rate. But when you're actually using this active approach of going on and finding what you need, it scales better than that. So imagine ultimately you had a 10,000 hertz video sequence of this. Things would move less than 1 pixel from one frame to the next. You would predict that, and your search process would be a case of going in and saying, tick, yeah, feature there, feature there. You'd be very surprised if anything wasn't there. It would be very cheap just to check that things were as you confirmed. And maybe it would even say on some frames, you don't even need to bother looking at this image. We're so positive about what the answer will be that there's no point even looking at it. So we've started doing some implementation of really high frame rate systems. So this was together with Peter Kaminer, who was visiting me last year. So far this is pretty straightforward. We've just kind of run MonoSLAM very fast, basically. So the interesting part of this video is here, where here you can see the frames, and this is 200 frames per second. So virtually everything that you've seen there happened in a second. So he was kind of shaking the camera like this, but doing smooth, continuous tracking of its position. So the interesting point here is that these search regions even for this vigorous motion at 200 hertz, you can make pretty good, even on a fairly uncertain motion model, you can keep your search regions small. So the image processing cost stays fairly cheap. So you can run real-time vision at 200 hertz. So that's an idea that we're very much going to be looking at. So in that kind of direction, and related to this idea of top-down image matching, we've done quite a lot of work recently on really thinking about that more theoretically. So just to explain this bit briefly, I'll just switch for a second to a slightly different presentation. Sorry. Yeah, so we're thinking about matching features in images, and we want to, deal with all the things that we can normally deal with, so ambiguity, mismatches, and so on. So we've come up with a way of coming up with global consensus matching in a sequential top-down way. So this is what we now call active matching, and then we've got a paper that's going to be in ICCV next month. So how does normal matching work in structure from motion or other systems? You find candidates by doing bottom-up processing. So you detect all the features in this image, you detect all the features in this image, and then you match them up based on some initial cue like appearance. So the ones that are fairly close in image space have fairly similar appearance. You match them up, and then you try and work out which are the good matches and which are the bad matches. And you do that with RANSAC or something similar, which basically searches for global consensus. So which set of those matches are consistent? They're all telling me the same thing about how the camera moved, for instance. So we find candidates and then we resolve them. So the approach that we're proposing, so another method for doing that, which is a bit more probabilistic, is something called joint compatibility branch and bound, which I did have running in the demo I was just showing you there. But the other kind of approach that we're thinking about is really guiding that search. So can we measure the features one by one and use the fact that every time we measure one feature, it tells us something about where to look for the other features. So I did some work about 3 years ago on basically sequential feature search, but in a simplified case where there's no ambiguity. So imagine you've got this problem. You're trying to track an object. So it's an object that has 3 degrees of freedom and slide around on a plane. There are certain positions on this object where there are features you can measure. So based on your uncertainty about where that object is, as you get this new frame, so last frame plus a motion model, you've got these search regions for your features. So this is saying this object, there's some uncertainty about its XY position, there's quite a lot of uncertainty about its orientation. So therefore these are the uncertainties on the positions of these features. But the interesting thing is that these uncertainties are highly correlated to each other, and they nearly always are in most matching tasks, because most of the uncertainty in where you'll find the features is due to uncertainty on camera position, for instance. So you can think of a step-by-step search where, for instance, you measure this one first. That wasn't going to work, I'm sorry. Okay, so actually we measured this one first. So that meant we searched this region here, we found actually a correlation match for our feature here, and then based on that we update our estimates of where all the other features are. So we map those correlations into all the other features, and so we've got blue is old, red is new. So all of these other search regions have shrunk. So now we can go and match our next feature. I can't remember which one it was.
Doesn't that imply a matrix update?
It does, yeah. So this is this trade-off. We've got this relatively expensive update of this distribution over these features, but then we've got very, very cheap image processing. So we search this feature next. So basically, after measuring these two features, we've pinned the object down pretty well. All of the other features now have very small uncertainties, so then we can pretty much go and check them off. So I should say that these numbers you can see here are actually information-theoretic scores. So these are numbers in bits that say how many bits of information will measuring this feature give me about the position of the object. So this enables us to define this very nice, rigorous kind of strategy for doing this search.
So you take the biggest one?
Well, you either take the biggest one, or maybe you take the biggest one divided by the number of pixels you've got to search, or something like that. So there's different strategies you could think of. So just to show you now the extension to that now to a practical problem. So instead of using a single Gaussian representation, we use now a mixture of Gaussians representation, and we can now cope with ambiguity and tackle real image sequences. So here's an example from MonoSLAM. So here's a certain frame that we capture. These are our predictions coming into the frame. So in this example, we've got a bit more motion model uncertainty than we did in the live demo. So the ellipses are a bit bigger. Information theory tells us which of these features to measure first. So it's chosen this one. We apply our correlation matching over this, and it gives us two possible matches within that region. So what do we do on the basis of that? We update our other features, but now we've got a mixture of Gaussians model. So if you like, we have three discrete hypotheses here. Either that this was the correct match, that this was the correct match, or that neither of them was the correct match. So each of those now branches off into a Gaussian. So we've got three Gaussians now with weights that add up to 1, representing our belief about where these features are. So each of those Gaussians is a joint distribution over the positions of all of these features. So our next step is now to choose another one of these features to measure, and to choose one of the Gaussians to measure. So the next thing we decide to do is to measure now this feature within this small region. So what actually happens now, so we've kind of guessed that this was the best one, or that there was a little bit more method to it than that, because this one was matched closer to the center of the Gaussian than this one. So this one actually had a higher weight anyway. So information theory has told us that the very sensible thing to do now is to check out whether this is right or not. So we choose another feature, we search as if that was the right hypothesis. So we've searched this very small region and we found something. So before doing this, the weights of, we had these two smaller Gaussians with quite similar weights. But once we measure this one, that's kind of rubber stamping that Gaussian. It's predicted this smaller region for that feature, and it was actually there. We have models for false negative probability, false positive probability for every feature, and so on. So actually finding that feature is now very good confirmation. And we've now basically resolved most of the ambiguity here just in those measurements. So the probability of this Gaussian has gone right up to 0.99.
How do you actually calculate this information theoretic measure?
It's basically mutual information. So you, I probably should talk about it later because it's quite detailed, but you basically look at the mutual information of the distribution before and the expected distribution afterwards. But it has very nice properties actually, because it turns out that the mutual information, you can decompose it into a discrete component and a continuous component. So basically, you've got this mixture of Gaussians distribution, and what you'd ultimately like is a single kind of spiked Gaussian. So if you make a measurement that will tend to take two Gaussians with similar weights and change them to more like this, you can think of that as a discrete. It's changing the probabilities of a discrete histogram from something like this to something like that, so you get an information gain. That's one thing. Resolving ambiguity is gaining information. But you also gain information by increasing precision. So if you have a fat Gaussian and you make a measurement that reduces it to a thinner Gaussian, then that also gives you information, and you can evaluate the number of bits. So basically every time you halve the standard deviation of a Gaussian, you get 1 bit of information as well. So the very nice thing about this bits measure is you can just add those two things up, and I think it's very rigorous. So therefore the rest of the search now is really straightforward. We've knocked out the ambiguity, and then the rest of the features we pretty much just have to check they're where these very precise predictions are telling us. So the kind of most interesting result here is that we get the final matching result, which is correct. And if we compare here the number of image processing operations that we've had to do in active matching compared to what we would have normally done in MonoSLAM or in any kind of detect first then resolve, we've reduced the image processing operations by a large factor. That's not necessarily to say it's faster overall. In fact, it is. This does run comfortably in real time, and it's pretty fast. But I don't know yet how this scales to more features and everything like that. But I find this very promising. Okay, so we'll just go back to the main talk and finish off. Should I be wrapping up very soon, David? Yeah. Yeah. Okay, so I've talked about looking for increased performance in the area of high speed and efficient matching and so on. Another thing you probably want to do is increase performance in terms of the size of area that you can map. So one of the big limitations of this MonoSLAM approach was always you couldn't move very far because we have an EKF over a set of features. It's relatively expensive to make a big EKF. So as the number of features gets too big, everything slows down. And also you lose accuracy because the linearization assumptions being made in the filter become worse as your map gets bigger and you get further away from this well-defined center of your map. So coming from the SLAM literature, people now understand well that when you're building big maps, it actually turns out that different parts of that map are relatively weakly correlated to each other. So there's high correlation within a local area, but the correlation between each individual feature in this room and each individual feature in a room on the other side of the building, you can pretty much represent that by a single kind of link between this room and that room, and divide your map therefore up into chunks or submaps where you do dense mapping within each one of those and then represent the links between them in a more approximate way. So we took an approach like this using MonoSLAM and made a map of a larger, so this is like a 300 meter loop around a courtyard where the different colors show the different submaps. And then we had a kind of recognition approach to then match them up at the end and then correct the trajectory.
How would you force it into one coordinate system?
Well, basically, once we've detected that this match and this map and this map overlap, then we've got an estimate of the transformation and the uncertainty between each of those maps. We just do a kind of optimization that kind of moves all of those a little bit.
Just the map links?
Yeah, just on the map links, yeah. Yeah, we have to do scale as well, yeah. Yeah, I think other people have done this probably better than this particular paper, but the general method is sound. So the other direction to really going is to think in really increasing the quality of the map in terms of density of representation. So I was saying that if the only thing you're interested in is camera pose, then it's okay for your, well, maybe it's okay for your map to be sparse. But in other situations, you actually want to infer something about the scene. So for instance, if you're doing robot navigation, then X, Y, Z position isn't everything you need. You if you want to actually close the loop and use that to control a robot, you need to do path planning, you need to do free space detection, possibly recognition, and all the other things. So I'm certainly thinking quite a lot about densifying maps and actually recovering surfaces. So there's several things which we've done which are kind of steps in that direction. So one is building maps which include both points and lines. So we haven't gone too far with this yet, but we've shown certainly that it's possible to accurately estimate the positions of lines as well as points within this framework. We also did some stuff to show that you can estimate the normals for the points that you're measuring. So if you've got relatively textured patches that you're measuring, every time you measure them, you can look at the different way that they warp in the image and use that to infer something about the orientation of the surface at that position. So here we're estimating the normals of the features. And then we're moving towards trying to do, dense kind of meshing of scenes, so to actually recover surfaces. So I do have a demo of trying to do that in 3D. So basically taking this fairly sparse feature map that you make from MonoSLAM and meshing it with textured surfaces. But to be honest, it doesn't really look very good at the moment, just because this map is so sparse that it's pretty ropey. So David actually has much better results on doing something like that. But even with your fairly dense feature maps, there's still quite a lot of parts where it looks ugly, probably. So I think there's a lot more work to do in that area. But something that we did do that was very successful was to think of a slightly simpler problem, where basically you've got a camera that's not moving in 3D but just rotating on a point, and then using the MonoSLAM type approach to do mosaicing. So this is a nice bounded problem where you can map the whole of a unit sphere with a fairly decent number of features, and this worked very well. I could just very quickly try and run that live, although this was seg faulting earlier. So basically I'll point this at fairly distant parts of the scene, because this is assuming the camera is purely rotating, so it doesn't like parallax. But if I just start tracking now, you'll see that it's detecting features in the normal way, but because it's assuming pure rotation, it's not estimating the depth of features, so it's mapping them onto a unit sphere, and then it's just grabbing triangles of texture from the image and then building up a spherical mosaic. So this scene isn't very great because there are areas with no features basically, but this will comfortably go all the way around in real time and build a spherical mosaic.
What are your requirements on picking features? Because even on that part of the wall where you don't have any, I could imagine you could track quite a lot of stuff.
Yeah. Yeah, you're probably right that the choice of features is much too choosy, I think, for this particular application. Yeah.
So you haven't tried insisting on some density of features everywhere,
and reducing your threshold in order to achieve that.
Yeah, well, I probably have tried at various points, but found that lowering the threshold on matching was throwing up too much kind of garbage, I think. But again, if you're imposing global consistency and so on, then maybe you could do that. So I know, Drew, you've done some very nice mosaicing stuff, haven't you, with more of an optimization approach. But yeah, but actually getting this running at video rate, I think, is a nice point about this. But I think you could also do the same thing with a kind of keyframes based method, no problem.
What happens if the features move?
Then you have lots more variables in your motion model.
Yeah.
The musical chairs, you can turn it on.
Well, I mean, so if features move with the system as it is, then what you hope happens is when they move away from positions that are globally consistent with the other features, the correlation will fail and if it fails enough times, it will automatically delete the feature from the map. So, but maybe your question was a different one. So if you...
The principle, the way to deal with it would be to say, figure out that some of the features are moving.
Yeah.
We can put them into the motion model too.
That's right, yeah.
But maybe that won't work because there'll be too many variables, I don't know.
I mean, you'd need to have quite a lot of, well-tracked features on every independently moving object before you could start trying to do that sensibly, I think. But something...
What's wrong with one?
Because one feature doesn't really give you 3D pose. But I suppose you could have a simpler sort of, like a layers model or something. But actually an application that we've been looking at where movement is very important is minimally invasive surgery. So in the group I'm in at Imperial, there's a large team doing robotic surgery and so on. And so they're interested in, putting cameras down, observing a beating heart, for instance. And we've tried some of this stuff in that area. And there are certain parts of the body you can look at that look kind of rigid and you can get a reasonable result. But actually, most of the interesting parts have this highly correlated movement. So we have started to think about, how you would model that. So you need to say that each feature isn't rigid, but presumably it's constrained relative to the features nearby, with some elasticity model of the tissue or something like that. So there's been recently some nice work on, doing structure from motion of deformable surfaces with offline kind of techniques, but I don't think I've seen anything doing real-time stuff with deformable objects yet. But yeah, there's beyond surgery, I always find it hard to think of good applications for where you'd actually want to map, deforming or moving things. But you wouldn't map. But you wouldn't map the players exactly. I think if you could solve there's always enough static things that you can see that you can. Well, then I think you just have something completely separate to track the other players. I don't think there's any need to do it jointly. But in the surgery application you do, because there's nothing static to look at in there. Okay, so I'm just about finished. I'll just show you one last application. So this is something I did 2 or 3 years ago, so just taking this software and applying it to a humanoid robot at the AIST lab in Japan. So we weren't closing the loop and controlling the robot or anything. We were just trying to estimate the motion with a single camera in its head. So the robot was just walking in a circle around the room. And then this was an output from our system where we're recovering so building a map of features, recovering fairly nicely this kind of side-to-side swaying motion that the robot makes as it walks, and then building a map all the way around, and at the end closing this loop up. So for humanoid navigation, something like this would be important, because these robots are pretty much walking machines until recently, and they have problems so the robot's got pretty accurate movement odometry, so when it makes a local movement it knows pretty much where it is, but if it's turned through 360 degrees it could easily have an error of 10 degrees or something, so you need vision to correct those kind of errors. Okay, this is a fairly rubbish video of some kind of medical stuff. Okay, so just finally to finish, I'd like to acknowledge the various collaborators that I've worked with on this stuff. And it's possible to download some of the software, although it's a version from a couple of years ago. Anyway, thanks very much. Okay, thanks a lot.